don't think anyone who doesn't know central limits theorem would confess now.
Okay.
In front of 23 other people.
Right. Okay. So that's very good. So that means I can start from beginning and can check whether what I say is correct. So we start with let's see, I have a pointer, I think. Right. So I start with a sequence of random variables. They are identically distributed. We normalize it. Average 0, variance 1, that's for convenience. The only most important one is the independence. Then if you sum them up from 1 to n, and then we renormalize this one by square root n, and this converted to the Gaussian distribution, right? So the this is one of the most sort of important theorem. The independent part can be replaced by something a little bit less independent called strong mixing condition. And the normalization doesn't matter too much. So we can remove it and renormalize it. So there are other theorems allow us to have the same type of theorem. You sum up divided by the square root of variance. That should look like a Gaussian curve. Now, what does strong mixing mean? Strong mixing means you take your random variables, you take a chunk of them, say, because stationary doesn't matter where you start from 0, right? You go to the past, you take that, you take something determined by something in the past, then you go into the future, you take the span of to be n. Then from the n onward, you look forward. So you take any two things, determine one from past, one from the future with gap n. Then the two events are independent if that object, this object here, is equal to that object. That's independent event. We want this to be, we look at the difference to see how not independent they are. Then we take supremum A and B with A from the past, B into the future, and take it and go to infinity. That's called strong mixing. Now, the second part, the important...
So do you need a condition on the rate to 0 of mixing coefficients?
It just need to be going down to 0.
Nothing else.
Right. Right.
Thanks.
No, just a second. I believe that's enough.
In book of Billingsley, whatever, there is some rate of convergence. Usually is a kind of power of n1 plus epsilon, something like this.
Right. You usually need to be rho of n to be, so you could some function for n, you want to be integrable.
Yes, that's exactly, because otherwise there are counterexamples in the book of Priestley, or not Priestley, but Bradley, yes.
Right, right. Yeah, so it's, you want it to be something 1 over n to the 1 plus something.
Something like this.
Yeah. Thank you, Nicola. Very good. And so, yeah, you should keep checking with me so I don't talk rubbish. Here we are. So now we started with IID. Now we sum up the random variables, but instead of summing up n of them, we take a fixed number t, we take n times t number of them, and divide by square root n, then you get converged to Gaussian with variance t for each t. Now that's the central limit theorem we just talked about. Now recall what a Brownian motion is. A Brownian motion is a Gaussian process, means you take any number of times, the joint distribution is Gaussian, multivariant Gaussian, and each time t is Gaussian with variance t. And the most important, if you take the increments of the process over non-overlapping intervals, they're independent. Now, Danska's theorem says the WTN we defined earlier, when t changes as a process now, the process converges to the Brownian motion weakly on the continuous space of continuous functions. Okay, so that's one of the most fundamental theorem when we go from random variables to continuous versions. There are, the one I just give you is called, is a piecewise constant way getting from n variables to a path. The piecewise linear is another one. So take the points and linearly interpolate it. So they don't make too much difference at this moment. Now, this scaling we gave, look at the square root n. Now, this is very important. That means that if we scale the t by something, you have square root of this something come out. And that make the limit a self-similar process. And the self-similarity is exactly this scaling. Now let's look at what are self-similar processes. If you have stochastic process, speed or decrease the speed of it by c, this process should be distributed as the original one multiply c to the power h. Now, self-similar processes are very important because just like a Gaussian process, like a Brownian motion is a universal limit for independent random variables. And self-similar processes are another type of universal limits. For random variables, they are much more dependent. Like Nicola said, if your relation between how unindependent become, if that doesn't decay fast enough, and that's going to cause some trouble, in the sense we cannot convert it to a Brownian motion. But we do convert it to a self-similar process. And then you would have to, the self-similar exponents is exactly how do you scale. If you scale too much, you get a trivial limit, you get 0. If you don't scale too much, you get infinity. That's exactly the correct exponent, give the right scaling. Right? So they are quite important in mathematical physics. Let me give you a couple examples of similar processes. We're thinking about the increment. So you take 2 time intervals, you look at the difference of the process, and look at the correlation of difference. It's called autocorrelation. Imagine it's stationary. We assume the increments are stationary, and suppose it to be the order t to the power 2 minus 2h. And this one, h, sorry, I should have t to the 2h minus t. So I'll have a minus sign here. And so h is smaller than 1, this decays to 0. A fractional Brownian motion is one example. Is basically if you want this particular correlation, you want a Gaussian process. And with is continuous fractional Brownian motion is what we have. Now, we want to keep the same similarity and correlation relation. So we want to go down to a non-Gaussian process. Those are the Hermite processes. So how are they obtained? They are obtained by a kernel. This is object, and that's function for t. And then inside, there are some S around. I think I missed some SJs. There are some S around. Oh, no, sorry. No, there's no S. Yeah. So you have this kernel. Then now this is the function for lots of C1, Cn's. Now we integrate with respect to a winner process, dWC1. So winner integral, so if you want to integrate Fs dWs, called the winner integral, if F is smooth, just integrate by parts, everything would work. Okay? So anyway, this is Ito winner integral iterated m times. And this kernel is quite important. So there's certain race here, and it's a power. It's the averaging process. You're averaging your winner process weighted over the time. Now this is called the Hermite process. There are some scaling constant here. It's not these are not too relevant here. If m equal to 1, you have it's just one integral, that's Gaussian, and that's a fractional Brownian motion. M equal to 2 is Rosenblatt process. Then we get the higher order processes. Now let's have a more careful look at the fractional Brownian motion. As we said, it's Gaussian, stationary increment with Gaussian structure, which is determining everything. Now, if we look at the increments, so we take size h is the increment. You like interval separation t. Then the covariance, sorry, the what's this called? The covariance of the two increment is this power t to the 2h minus 2. And the h is not too relevant at the moment. Now, the fractional Brownian motion has this similarity property as well. Now let's see how do we see that from of a central limit theorem. Or it's actually called a non-central limit theorem. Traditionally, you say you have a central limit theorem. If you rescale your sum, you get a Brownian motion, you get a Gaussian. This particular one, let's see how it works. We have a stationary Gaussian. We look at the correlation called R of n, and that decays n to the 2h minus 2. If h bigger than a half, and this is non-integrable, this summation over n, the correlation, and this equal to infinity. This is called a long-range dependence. So if h bigger than a half, you have I could non-central limit theorem, but Brownian motion is Gaussian at each time t, they have correlation. And for now, it's not really non-central limit. Let me call it non-central limit theorem for now. And it's you take the summation, then it comes down, what's the correct scale to rescale it to get a non-trivial limit. And the correct scale is n to the power h. Okay. Then this will converge to a Brownian motion with parameter h.
Fractional Brownian motion.
Yes.
Brownian motion.
Yeah, fractional Brownian motion. Excuse me. Yeah, thank you very much, Nicholas. Right. And so I think lots of people worked on this. I'm not going to give you all the references. Not that I think Dobrushin, he worked. He was statistic mechanics from Russia. So Dobrushin worked a lot on it. Dobrushin major also. Now, the self-similarity, as we say, comes exactly from this scaling.
But Murat Taku was first who proved this theorem. Murat Taku from Boston.
Oh, okay. I'm going to ask you for that afterwards.
Okay, so
yeah.
Yes.
So let's see. Now let's see why I'm interested in this sort of theorem. So that's a question at the heart of problem I'm very interested in. Is called a multiscale problem. Multiscale could have scales in space and scales in time. We are talking about scale in time. For this, we mean you have something running on the clock. It's lifetime, like our lifetime. And then you could run a clock against somebody else. And when they compare to your clock, you might be faster than the other one. So there's a separation of a time scale. These are very natural phenomena. One of them is the following. We know that Brownian motion become popular because Albert Einstein used this model in 1905 what he did, he said, if you have an object in the water, and we know by Brownian motion, the observation Brownian motion, you put the water at rest, but you still see in the microscope that the particles, anything impurity inside, they're moving around. They come from the atoms, collision, and bump into them. So it's called diffusion. And Albert Einstein used the heat equation to describe the diffusion. And this is now called the Brownian motion. Now, in his setup, the Brownian motion will not have a velocity because the particle is not differentiable in t if you fix a sample. Now, not everybody is happy with this model. Well, they are happy because Peru, 3 years later, has conducted experiment with Albert Einstein's precise measurement and computed the Boltzmann constant and verified atom theory. So it is a very verified theorem. But for physicists, if they want to say that, look, I want something with physical. Physical is something I can measure, a speed. And this one I cannot measure speed. Now what do? They said, let's approximate the Brownian motion by something which is physical. The ones physical they did is saying, let's say you have something has speed, but the speed is unphysical. The speed is given by a Brownian motion here, and the friction coming from V, and this is called the Langevin equation, the full Langevin equation. I have scaled it with 1 over epsilon. And this scale is not a diffusive scale. It's not just that I change time. But if you rescale space as well, then you see a rescale space and rescale time. That become a homogenization problem. The moment, let's see, how do you see you have a limit? It's quite simple. You integrate this equation x epsilon. It's the integral v epsilon. The integral v epsilon is here, and which give you this, you put epsilon on every side. This, if your v is nice, it's converted to 0. All you see is Wiener process. And this is also the famous Kramer's small Low-Trotsky limit. There's a very, very important scaling limits we use. We're going to see it again. So this, we are talking about when you take a homogenization problem in two scales, you want to break it down into two parts. Obviously separated. You can see a slow variable, let's call it x. Then you have something which moves in the fast scale, thinking about the velocity. And that typically moving, so typically is another process run over longer time, over 1 over epsilon amount of time. Now the question is, if you take epsilon go to 0, whether it's possible to approximate the slow motion by another one, which is governed by an autonomous equation. Here, it has an input from y. We want to throw a y away, have an autonomous equation. If you can do this, this is called effective dynamic. How can this happen? This happens if y, it runs very fast, but its effect is also, if it's also oscillatory, is running back and forth, its effect can get averaged and canceled out. When this happens, we grab what has been left over, the persist effect. And this is called transformed adiabatically into the slow variable. And this is what we want to do with the homogenization theorem. The typical theorem with this is to use a stationary strong mixing process to be the fast variable. Or we can use a Markov process with spectral gap. In either case, in the limit, the approximation would be a diffusion process, means that locally look like a Brownian motion. Now that's where this scaling 1 over square root epsilon come in. When you use that scaling, you get a locally Markov process or diffusion process. Now this theorem is very much at the heart of this theorem is CLT, central limit theorem. The one I gave you was for discrete time sequences. We could have a continued time version, and here is additive functional. You take V to be centered, right? If it's not centered, you get T over square root epsilon is constant, so you never converge it to anything. You have to remove that. So you make it centered, and then this guy would converge to a Brownian motion, exactly like in Danska's theorem. Now this theorem is, is very well understood, has been around for years. Now they are still around. The question is always, what's your environment, how they interact, and so on. There are very little has been done in the case which is not strong mixing process. There are maybe half a dozen papers did talk about this. Under conditions, your environment, okay, so F is the environment. So you have X, you fix omega, the YT epsilon omega is random, that give you an environment. Suppose the environment is isotropic in T, in X with certain decays. There's some theorems about this with a two-type result. One is converged to a diffusion. Second is converged to a fraction Brownian motion. Two results, about 5 or 6 papers on this. Now we are interested in fractional noise in general. Now we ask what happens. What is a general theorem of this type? It's called the target particle, because we imagine X is a guy like a buoy sitting in the ocean, and or sitting in the body of water. And the body of the water is turbulent or subject to random or any kind of fluctuation. So that's called the passive tracer problem here. Now, let's look at one of the functional central limit theorems for Brownian motion. We could, instead of as we already seen, if you have an Einstein-Uhlenbeck process, we said we need something has very much ergodic properties. It oscillates a lot, it's ergodic. Einstein-Uhlenbeck process is a very good one. It has a spectral gap in some sense. So you have this lovely convergence theorem to a Wiener process. Now I would like to think about it a little bit more. Look at this process. I'm taking W to be a Wiener process, and then your solution will be explicitly written by variation for constant formula. The point, look at the kernel. This kernel is smooth. That means actually your W doesn't have to be Brownian motion. When we say Brownian motion, because we want to use the Ito calculus, but it can be any basically function which is doesn't need to be differentiable, and this makes sense pathwise. So you don't have to use the omega there. Okay? So I'm going to use the fractional Brownian motion in a moment, and of course, if this guy here is not additive, everything changes. When I change into fractional Brownian motion, there's a problem. What is this integral? Before we go further, I also like to mention that this central limit theorem we see, this object has the same distribution as the one with the process we have speed up like this. Now, maybe it's time to take a little break. I was thinking why we are interested in a long-range dependent noise, whether you see it anywhere, the long-range dependent noise. And so this, the long-range dependence, when we say that you have the fractional Brownian motion, the increment process, you fix, say, the increment to be 1, but you like the beginning time to move, that's a process. That thing is had long-range dependence. Now, long-range dependence come from dependent variables, and these are often observed. If you see data network, exchange rate, anything which has a cycle, economic cycle, there's always a residue coming in from the past, which influence what is going on. They're not a mark of, they're not an independent increment. The best example is actually about the river Nile. The river Nile overflow and flood every year. And the flooding is the lifeline for Egypt, especially for the agriculture. So if you got too much flood, everything's destroyed. If there's not enough flood, there's not enough fertilizer, famine follows. So for a long time, the Pharaonic period, they use this water flow to compute the taxes. And a high priest's job would go down to one of these nanometers you go down the staircase, which is nicely marked, go down to the river to see how high it has come up the stairs. Then you compute next year what the water would be likely to be. It's random, but they see a correlation. Now, this has been observed later on by Harold Hurst to look at if you contract water dam and you look at how much water is remaining every year, how much go down and up, and he thinks it has a long range rather than independent. It depends on many years. He actually said to construct the dam in Aswan, you need 10 years. You need thinking about the dam good for 10 years. Now, later on, Mandelbrot and his collaborator Van Ness, they decided to model this so-called Hurst phenomenon with fractional Brownian motion. And he liked fractional Brownian motion, you know, he likes fractals. A stochastic process like fractional Brownian motion, self-similar, is rough, they're like fractals. They have self-similarities. It's sort of a self-similarity tell you some kind of persistent roughness. Okay, so that's enough for the digression. Let's see what happens with a long-range dependent process for fractional Brownian motion. We take say we take some Gaussian process. Now this is a thing different. We take a stationary Gaussian, normalize it, and give it a correlation relation as we would like n to the 2h minus 2, same as a fractional Brownian motion first per meter h. If the sum is infinite, it's called a long-range dependent. Then we already seen if HM here, this is a Hermite polynomials. They are constant for m equal to 0. M equal to 1 is just the identity function. For the identity function, we, I think I messed up, sorry. For the identity function, we already seen this one. If you scale it appropriately by this H star M, and H star M coming from M, which is the polynomial degree in your polynomial. Okay? Now I take M equal to 1, and it's just 1 over n to the h. Now this we already seen it converges to fractional Brownian motion itself. And if you want to look at the functions of this, now let's take the polynomials. The Hurst polynomials are good because they got if you look at the Gaussian, they are centered. Also, the point is, if you have something decays n to the 2h minus 2, if you raise xi transform by a Hermite polynomial, say degree 2, then the correlation, the new one, the autocorrelation, right? I'm not talking the past and the future. I'm talking only the 2-point autocorrelation. The autocorrelation would be increased by this m. If you take m enough, and the summation is going to be finite. If it's not enough, it's not finite. Okay, so suppose m is small. I think my slide is slightly mismapped, but what I'm saying is correct. If m is small and your decay is not too much, and then if you rescale it, we don't get a Brownian motion. We get a Hermite process with a self-similarity exponent h in the Wiener-Ito integral of iterate m times integration. And this is all really is, you sum it up, you divide it by the variance. You look at how the variance grows with n. That determines everything. And so that's what you get. And if you take your Hertz parameter, if you take your polynomial degree higher, and then you have a big decrease, and this is going to converge to a Brownian motion. Okay? So the two cases, they are basically square root n, tau is diffusive, or the borderline case square root n log n. Okay, so what we learned is these guys, even though in this case there may not be strong mixing, but you can still converge to a Brownian motion. And it's different from Brownian motion, from the strong mixing case. For strong mixing case, you can transform your function, your sequence by another function. It generically doesn't change the limit. Okay? Here it does change it. So in a nutshell, we just said you took a Hermite polynomial, you can take L2 function and write it down in terms of Herminomial expansions. We want it to be averaged to 0. So you start with at least one Hermite polynomial. The lowest of this one exists is called a Hermite rack. The lowest one determines the structure. If you transform your sequence, it determines what is the structure. So it behaves like HM. So then you would have a limit theorem for this guy. It as a converge to a Brownian motion or Hermite process, depends on the rank. Now, all of this converges in finite dimensional distribution, means that you take a time points, you look at joint distribution, and that converges. That doesn't tell you converges as a process on the space of continuous functions. So that's if you want to say converges on the path space, and there's lots of Mullivan calculus to be done, which has been done by some very experts in Mullivan calculus, Noada, Piccati, and Campis. So they did lots of this. The other thing is joint convergence, right? I take one function. So first, I give you the functional version of the CLT. You take one function, let's call it GK. And then you rescale it depend on the Hermite parameter. And that converges to something. Now I take a number of functions. We have a vector, a multivariant object. Now we will ask whether the multivariant object converge. And this does converge in two cases. One is if every component converge to Brownian motion. Two is every component converge to Hermite processes. And the third one is every component is Gaussian, which means Brownian motion and fractional Brownian motion. So that's what we know is in the finite dimensional distribution. Sometimes they are in space of continuous functions. Now, this is quite important. Why I'm keep on talking about where does it converge to? Because what I have in mind was this homogenization theorem. This people have been doing homogenization theorem for years. There's a set of rule. You use some kind of a martingale approximation, and then you know Markov process has a martingale characterization. And if you can prove that, you prove your convergence. Now, if you don't go to, your limit is not a Markov process for homogenization. There's not much rules. Nobody know how are you going to get that limit theorem. Now, one way to look at this, so is thinking in terms of the newest development called the rough path theory. We're going to look at something like a family's equations driven by, or the integrals with respect to a function, which is not differentiable in T. It's not defined by Ito integral. But you still want to understand what it means. In this rough path theory, there is a very nice theorem called the continuity theorem. It's saying, well, you have take your favorite ODE, x dot equal to fx, but it's not driven by dt, but you have a gt there. Okay? Then you say, okay, you allowed to change your integrand, you allowed to change your integrate. Then the solution depends on this. It's called the Ito map. For the Ito calculus, the Ito map is not continuous in the driver. For rough path theory, it doesn't use the theorem of a stochastic process that much. What it says is you take one sample, you look at your sample. Okay, if you take a fraction Brownian motion, for each, what we can do is we can find set measure 0, throw it away. Then I take a sample path, any sample path, and then I can transfer this sample path into rough path. What is rough path? Rough path is the following. You take your original process, you add in some secondary two-parameter process in. In good cases, it's like we're talking about a vector valued. So what you do is, for example, you integrate your first component with respect to the second component. So that's the iterative integral. And you can also integrate this many, many times. And that depends on how rough it is. Okay? So this, for fraction Brownian motion is done, is saying you can find such a universal map lifting up. You can define it by rough path theory. But within that rough path theory, it doesn't give you a good estimate. You cannot do this limit theorem just like that. But there are some tools you can use. So what we're doing is we take this, we're thinking this guy as drivers. And then we want these guys converge in a strong topology, the rough path topology. If we can do this, we can use the continuity theorem. Okay. So that's all I need to say. Let's see, I have not much time, so I'll just go a bit faster. I took a toy model is the Einstein-Uhlenbeck process driven by fractional Brownian motion, where we can, it's a funny one. This one, if you take from any two starting point, the two solutions converge exponential fast. But if you look at the solution, a particular solution, look at the autocorrelation, that doesn't decay. It remains the same of the original one. And so for this, for example, you can compute, and you look at the Hermite polynomial, HM with Y0, and HN evaluate YT. And by typical theorem, you know it's actually given by expectation of Y0 YT to the power M, if M equal to N. That's where the Multiscale calculus, the Gaussian is very important here. then you could look at one of the most important indicators is this double integral, is how does it behave? And high Hermite one, it behaves like square root t over epsilon because the integral is finite. Otherwise, you have it behaves differently. Right? So this determines your constant. You should be really scale it. So in this case, we'll have the right scaling for this. What with Johann Geheringer is a PhD student here. We prove the following theorem: is that supposing you take your d1, dk, several functions, they have a rank. The better the rank, it decays faster. I take the high, put the high rank in the beginning, the low rank later. So the high rank part, the low rank part, and they converge jointly to something. Here is joined Brownian motion, so Wiener process. That part is Hermite. We know that the two parts are going to be independent. The correlation on the Wiener process is completely given by this Kubo formula. And the other part is quite pretty because the Hermite process can be written down as integral representation with respect to a Wiener process. And their correlation is given in the following. Each of them are given by the same Wiener process. So this is sort of what we prove this convergence in Holder space. But this, okay, you have to prove some joint convergence, not too important. The most important is now we're going to define so-called canonical lift of the process X, the integral of these guys. Right, this guy. You see, this is the integral with respect to t. It's differentiable. It's very nice and smooth. So we can take the increment, the S increment, integrate with JC increment. This is the first iteration of iterative integral. Because h bigger than half, all my fraction Brownian motion and everything is Holder continuous up to half. Then the first iteration is important. So we take this, it look like this. Now we say, oh, that looks really good. That's like what other people been doing so far so much. But what is so important about this guy? We're going to look at them at this topology. We look at the Holder topology of the increment and the Holder sort of hold distance for these guys. If we can prove they converge in this topology, and then everything's good. So what we did is prove exactly the convergence of this guy to a rough path. So you can have X, it's a secondary process, can be given like this, and this, you can specify it if the S component, J component, the limit of each of this limit, if one of them goes to Hermite process, you get a Young integral, otherwise Ito integral. Young integral means Riemann stager. So this is the theorem we proved. So now the application is the following. If I take a homogenization problem, but I take a product form. Remember before, I'm interested in this guy, but I can only do a polynomial sort of form if we take this object, but then we put this together with that, and that's the driver. We have to prove the driver converges in certain topology, then the solution is continuous. So we prove xt epsilon converge to solution of this equation, and that's a new type of theorem. Is sort of driven by Hermite processes of same Hurst parameter, but with different complexity. Okay, so I'm sorry, I'm a little bit slow, and I'm done with my talk. I think. Do you?
Thank you very much.
Thank you.
Thank you.
So do we have any questions?
Thank you.
I mean, can you replace in your theory Gaussian process into something related to gamma process, let's say chi-square, for instance, sum of independent square of Gaussian, and Hermite polynomials into Laguerre polynomials, and basically
yeah, so
how important Gaussianity? I mean, in my view, you can definitely generalize what you did for let's say gamma correlated random field. When we have sum of square Gaussian sums, then Hermite you replace Laguerre. Here will be not Hermite processes, but something related to Laguerre processes, which are kind of sum of Rosenblatt processes, something like this. So that's my view.
right, that's a very beautiful question, because I have been thinking about it. Of course, that's what we've been hoping to do something. First Gaussian, we couldn't even do a general Gaussian. There's a way to do it. Is for the fractional or instant Ollenberg process, we can do it. Okay. For Gaussian, we have pathway. As you observed, we transfer the correlation by Hermite polynomial. Now, I haven't thought about the gamma distribution. I think that's a beautiful suggestion.
You have all components, you have all necessary components, analog of the limit theorems, non-central limit theorems for this. That's definitely doable, in my view.
For sure. I would definitely want to look into this. And that's one thing it's fantastic. I would ask for some reference from you, if you could, if you have some good references as well.
Yes,
so this is certainly, we hope to do that. Yeah. Of course, for that, I would know what are the self-similar classes for it as well.
Yes, here will be situation like somehow, I mean, first Laguerre polynomials is sum of second Hermite polynomials. Basically, you will only build a theory up to the level, let's say m equal to m Hermite rank. But I mean, some sort of Laguerre rank will be kind of 1 and maybe 2. And it means that Hermite rank will be either 2 or 4 and not more. So you have some restriction here, but well, I will send you references and papers. That
would be lovely. That would be lovely. From our point of view, we want to do two things. First, to do a general Gaussian to see what sort of a condition I can have a chunk of stupid conditions wish list put in. That's not what I want, right? I want something workable condition which such that this holds. The second one is we want to know if it's not a Gaussian. Of course, if the limit is Gaussian, and then we could approximate it by rate of convergence.
Yeah.
Then the question is really not Gaussian, but is driven by some process we can control locally. So can we? So it's a solution for equation. Can we do it? That one I found that I don't know yet. And then the very difficult one, I think the other question is this guy. So, you know, in the non-product form, this guy, the one we just done it is, say the driver put alpha with G. If I just have non-product form, we think we have to go to infinite dimension to work on it. I don't know. And I don't know how do you play the different scales. See here, we got different scales in the same equation. Yeah. We don't know how to do it. So that's certainly a lot of question about this. Maybe since you have some useful feedback, I should tell you the other problem we were interested in is not the homogenization is generically a two-scale equation here. So where you don't have the G only, you have some genuinely randomness there, which is not a Markov.
Yeah.
And to see what are the effective limits as well. It's two different questions because this question is really the structure of the fast variable. The other one is more the problem of the slow variable, because slow variable now is a fractional Brownian motion a little bit.
So it's very, probably it's very, we are very narrow now problem. Maybe some other people wants to ask, because if I have something to say, but it will be a very narrow discussion about.
Yeah.
Maybe you have to go to fractional calculus basically, and to find example among the fractional stochastic differential equation in fractional derivatives. Then it will give you, because the fractional derivatives usually self-similar, and basically you can find some sort of both how to replace in terms of the, like, let's say Fokker-Planck language, both time and space simultaneously, and fractional calculus you can see how to do it. But anyway, I think it's very narrow. Let us some other people to ask you, because it's some sort of.
No, this is good, because what we did is we used again some kind of techniques in not in raw path, but from raw path related theory, reiterated this integral. What we did is we instead of using rough path integral, which doesn't work, you know, there's a sense that, okay, for h big and a half, you can use a rough path to define it. You can use a fractional calculus to define it. What we did is completely different. We said that you can define this, it makes sense. We have to sort of locally approximate. We take a small time scale for the slow variable. So then we approximate these guys by a Wiener integral. We make them sort of more or less conditionally independent. We define that. And that allows us to give lots of estimate. So you can throw it into calculus in and you can do it.
Okay, thank you. Sorry, I don't want to take your time. Maybe some other people want to ask something, because it's very specific discussion here.
Are there any more questions that people would like to ask?
Well, maybe directly related, but because you mentioned these interesting facts about Hurst and discovering the time series analysis of the ancient Egyptians, is it known whether they actually were able to forecast using probably some correlations in their data the flooding of the Nile, and what method they used?
They use some adjusted, some kind of correlation function. I must say, I didn't look into it. I'm a little bit in doubt we could give more input to that. They are very, very well developed. This theory I'm talking about is really embedded in the fast, slow motions. If there's no fast motion, there's no complexity from, the complexity is different from what we are discussing here. In fact, I should do a bit more, but this one, it is lots of the raw motivation from statistics. I don't know actual application of this. Unless there are data coming from, you do have these 2 time scale objects. Hi, Federica.
Hi.
So far, there's only 2 Nicholas asked questions. Anybody else called Nicholas?
Okay, I don't see any more questions. So first of all, I'd like to just make a small announcement to remind people what's going to be happening with this seminar over the next few weeks. So next Monday, our speaker will be Christiane Tretter from Bern. The Monday after that will be Camilo De Lelis from Institute of Advanced Study. Then we'll have a 1 week break because it's a bank holiday. Then we'll have Jeff Kalkowski from University College London on the 1st of June and Julio Skaplunov from Kiel on the 8th of June. So that's the program for the next few weeks. It's on our webpage. And now I'd like to ask you all please to thank Xue-Mei for her talk today again. Thank you very much.
Thank you.
Thank you very much for that.